Welcome back for a second lesson on matrix LU decomposition. In this video, we'll use Gaussian elimination and a shortcut to determine the LU decomposition. The goal of LU decomposition is to write a square matrix A as the product of matrix L and matrix U, where matrix L is a lower triangular matrix and matrix U is an upper triangular matrix. For the shortcut method, our lower triangular matrix L will have a main diagonal consisting of 1s, and all elements above the main diagonal must be 0. For the upper triangular matrix, all the elements below the main diagonal must be 0. Notice for the upper triangular matrix, the main diagonal does not have to consist of 1s. In order for this decomposition to be possible, matrix A must be able to be reduced to row echelon form, which would be matrix U, without interchanging any rows. Also, matrix L and matrix U are not unique, and because we're using the shortcut method, we're going to be using the opposites of the multipliers used in the row operations to obtain U to build matrix L. So let's take a look at an example. We want to determine the LU decomposition of the given 3x3 square matrix. So we want to perform row operations on this matrix to obtain a upper triangular matrix, which means we need a 0 in this position, and this position. Let's start by obtaining a 0 in this position here. We want to add some multiple of another row to row 2 to obtain a 0 in this position here. So we can replace row 2 with 2 times row 1 plus row 2 to obtain a 0 in this position. Let's go ahead and do that. First row stays the same. Second row would be 2 times 1 plus -2, that's 0. 2 times 4 plus 8, that's 16. And 2 times -3 plus 5 is -1. Third row stays the same. Now to perform this row operation, we say our multiplier was this +2. This +2 helped us to obtain a 0 in row 2, column 1 of this matrix. Well, if we look at our lower triangular matrix, here's row 2, column 1. This element is going to be the opposite of our multiplier. Well, the opposite of +2 is -2. This is how we're going to build our lower triangular matrix. We'll always use the opposite of the multiplier used to obtain the 0 in the specific position. Now that we have this matrix, let's obtain a 0 in this position here. So again, we want to add a multiple of another row to row 3 to obtain a 0 here. Let's replace row 3 with -3 times row 1 plus row 3. First two rows stay the same. For the third row, we'll have -3 times 1 plus 3, that's 0. Here we'd have -3 times 4, that's -12, plus 4, that's -8. And then here we would have -3 times -3, that's +9, plus 7, that's 16. For this row operation, our multiplier was -3. -3 helped us obtain a 0 in row 3, column 1. Here's row 3, column 1 of our lower triangular matrix. The opposite of -3 is +3, so this element is +3. Now let's obtain a 0 in this position here, which is row 3, column 2. We need to add a multiple of row 2 to row 3 to obtain a 0. Well, half of 16 would be +8, so let's replace row 3 with 1/2 times row 2 plus row 3. Again, our multiplier is a multiple of another row that we have to add to the given row to obtain our 0. So here the first two rows stay the same. 1/2 times row 2 plus row 3, 1/2 times 0 plus 0 is still 0. 1/2 times 16 is 8. 8 plus negative 8 is 0. Now here we have 1/2 times negative 1, that's negative 1/2, plus 16, that would be 15.5, or let's say 15.5. Notice how we now have an upper triangular matrix. We'll call this matrix U. And then to complete our lower triangular matrix, notice how our multiplier in this case was positive 1/2 to obtain a 0 in row 3, column 2, where this position here, the opposite of positive 1/2 is negative 1/2. So now we have our LU decomposition. Here's matrix L and here's matrix U. So to put the pieces together, we know A equals L times U. Here's matrix A, the given matrix. Here's the lower triangular matrix. And here's our upper triangular matrix. Let's go ahead and take a look at a second example. Let's start by obtaining a 0 in this position here. Again, we need to add a multiple of another row to this row to obtain a 0 here. So we're going to replace row 2 with negative 1/2 times row 1 plus row 2. So the first row stays the same. For the second row, negative 1/2 times 2, that's negative 1 plus 1, that's 0. Negative 1/2 times 4 is negative 2 plus negative 4, that's negative 6. Negative 1/2 times negative 4 is positive 2 plus 3, that's 5. Third row stays the same. Our multiplier is negative 1/2, so we're going to put a positive 1/2 in row 2, column 1 of our lower triangular matrix, which is here. So this element is positive 1/2. To obtain a 0 here, let's replace row 3 with 3 times row 1 plus row 3. First two rows stay the same. Then for the third row, we have 3 times 2 plus negative 6, that's 0. 3 times 4 plus negative 9, or 12 plus negative 9 is positive 3. And 3 times negative 4, negative 12 plus 5 is negative 7. Our multiplier is positive 3, which helped us to obtain a 0 in row 3, column 1. So this position here in the lower triangular matrix will be the opposite of positive 3, or negative 3. And then for the last step, to obtain a 0 here, we'll need to add half of row 2 to row 3. First two rows stay the same. So 1/2 of 0 plus 0 is 0. 1/2 of negative 6 is negative 3 plus positive 3, that's 0. And then we'll have 1/2 times 5, that's 5 halves, plus negative 7, which is negative 14 halves, which would be negative 9 halves. So this element here is negative 9 halves. Notice our multiplier here was positive 1/2 to obtain a 0 in row 3, column 2. So row 3, column 2 of our lower triangular matrix will have an element that's the opposite of positive 1/2 or negative 1/2. So here's our upper triangular matrix, and here's our lower triangular matrix for our LU decomposition. So putting the pieces together, we know that A equals L times U. So A is the given matrix, L was our lower triangular matrix, which we built using the shortcuts, and U was the upper triangular matrix, which we found by performing row operations. Okay, I hope you found this helpful.